Hey gang, how you doing? Oops, forgot to pause there. How you guys doing today? Happy Thursday. Happy Thursday. Oh, I'm in the wrong window here. There we go. Let's try Canvas. That'll be the right tool, right? Got a couple things going on today. We're gonna try and not make my computer be so upset. The internet was great like all day, and now it got flaky again, like right at the end of my last class. So we'll see. We'll see. I'm hoping it's steady. Things are looking decent. My connection's not great though. That's no good. Maybe that's why. Yeah, it's not a great connection. Should be enough though for, 2000 kilobits. Maybe not. Nope, it's dying. Shoot. Technical trouble. Hang on. Please. We'll see. See what's up with that. All right. Trying here. Let's see. Looks stable. I didn't have to kick it too hard. How's it look on your guys' side? Is it laggy, bumpy? It's not doing too bad? We'll see. We'll give it a try. Fire up PyCharm. We did the basics of recursion on Tuesday. I wanted to say yesterday, but yesterday's wrong. On Tuesday, we're going to take it a step further here and do some more interesting recursion, and then talk about your first individual project. Thanks, Canvas. Cool. Stop. Okay, cool. So someone got in Lab 0. That's good. And then a couple people were able to finish that Chapter 2 quiz. That's due tonight, 11:59 p.m. or so. Again, open book, open notes, start it, close it, open it, start it, whatever. Just don't talk to your neighbors about it, please. And we'll go from there. All right, I think the bitrate's stabilized. That's good. We'll see. It still says my connection is not great, but we'll keep our fingers crossed. You know what might help? Let me get chat here on my phone instead. And that might be better. Because sometimes watching it here just eats my CPU, which is unfortunate. Let's try that. Come on. There's my stream manager. How do I close that? There we go. All right, so I got chat on my phone here. I'm just going to close that one up there. See if that makes that any better. That look a little better? Okay. There it is. Yep, so we're going to finish up recursion, and we'll talk about the first project we're going to work on here. Okay? Get PyCharm open. All right, and you know, I'm going to start up another project here. So I'm going to go through a recursive puzzle that I'm fond of. It's called N Queens. This is a great puzzle. So the idea with the N Queens puzzle, and usually it's 8 queens, but we can do N because we're fancy, and you know we all love math, is that we need to find a position on a chessboard in which 8 queens can be on the board and none of them threaten any other queen. So this is one particular solution here. Remember, a queen in chess can attack anything in its row, anything in its column, and any of its diagonals. So let me actually, maybe I'll fire this up here. So maybe I'll steal that picture too. Any of them, right? We can take any of these pictures, I'm sure. There we go. Nice. Okay, now I can draw on it here. So a queen, right, can attack anything in its row, anything in its column, and any of its diagonals. Okay? So this queen here on A is safe. We're not attacking any others. The queen here on B, let's see, nothing in its column, nothing in its row, and nothing on its diagonal. So it has all of these diagonals to have to check. Right? Okay, the next one here on C, nothing in its column, nothing in its row, nothing in its diagonals. Boom, boom, clear, and clear. So if you can imagine, we want to write an algorithm for how to solve this. So before we even get into code, we're going to figure out how we solve this. Let me take off all those lines here. Look at that. Undo, 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 undo. There we go. Got it. Okay. So to see if a problem might be solvable with recursion, we have to do two things, right? The two things. One, you have to identify the base case. When is the problem solved? Well, in our case, when queens equals 8. When I have 8 queens on the board, I win. I'm done. Problem solved. Can't get any simpler than that. Okay? Try to make that a little bit nicer here. Sorry. Queen N. There. This one's Python today. So that's my base case. Right? So that's the base. The other base case, there is possible to have another base case. Right? This is one. There also is another base case where we can't put a piece in. Put a queen down or on the board. Sure, we can't put a queen on. So either one of those, right? This one we win, this one we lose. But they're both base cases. You can't get any simpler. Okay, what we can do though, the second thing you have to be able to do is approach the base case. So what do we do to get closer to that base case is we put queen on the board. Right? I don't know if you can see that. Sorry, I forgot my webcam's over there in the bottom right. Okay? So that's all we have to do. So, and we're going to do this in a certain sequence. So what we need is we need a two-dimensional array, or 2D list, right, to represent the board. 8 rows with 8 items in each. And the naming we don't actually care about. We don't have to name them at all. It's not a problem here. Right, so we're going to build out the board here, right, which is a list of lists. Boom, 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 right, on and on and on, doing this 2D list thing, and so on, right? And eventually we'll put a queen in. So that's not 8 of them, but that's okay. You can imagine we'd have 8. And you can do this with any n. I think as long as you have more than 4, I want to say. Maybe 5. I forget. It's not all that important. But you can go bigger, is at least the idea. Okay, so what we're going to do is, I like the idea of going column by column. You can also go row by row. But either way, it's essentially the same thing. So let's get all of them in here. So that's 6, 7, 8. Okay, and each of these then has some spots. 1, 2, 3, 4, 5, 6, 7, 8. Right? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. You guys are bored of hearing me count to 8 already. I'm sorry. I guess I should have just done an empty chessboard. That would have been prettier. Okay, there. And now remember, 0, 0 is up here, right? Row 0. Oops, sorry. In Python land, right? Nope. Why is my arrow in the wrong spot? 0, 0 is 0 row, 0 column. So that's 0, 0 right there. Right? So what we want to do is we want to try and put a queen down. Okay, that's what we have to do, right? That's how we're going to approach the base case, is try and put a queen on the board. So we're going to start at row 0, column 0, and see if we can put a queen down. So can we put a queen there? Sure. Queen. Done. Now what I'm going to like to do is go to the next column. So I'm going to go to the next column. This is my working column. Oops, keeps messing up there, I'm sorry. Right here. Right there. So now I'm going to say, can I put a queen at row 0? No, because there's a queen behind it. Can I put a queen at row 1? No, because there's a queen on its diagonal. So that's no good. That's no good. Can I put a queen here? Sure, I can put a queen here. Let's put one now. Let's approach the base case. Great. Now we're working in this one. Can I put a queen here? No, because there's already one in that row. Can I put one here? No, because there's on a diagonal. Can I put one here? No, it's on the same row. Can I put one here? No, it's on the diagonal. Can I put one here? Sure, put one here. Okay, go to the next column. Now I have 3 queens on the board. I'm approaching the base case of having all the queens on the board. I can't put one here. Can I put one here? Yep, this one's open. Right? There's nothing in the diagonals. And I'm going to give you a little hint here because I've done this a couple times. You never have to look forward, because I know there's never going to be a queen in front of me. I only have to check the diagonals behind me. Right? So I need to check the row that I'm on and the diagonals behind me, because I know I'm only putting them on column by column. So there's no point in checking the column, and there's no point in checking in front of me, right? There's nothing ever going to be in that direction. So I only need to check behind. Okay? So that one's good there. So then we go to the next column. Can I put a queen here? No. Can I put a queen here? No. Can I put a queen here? No, it's on the diagonal. Can I put one here? Let's see, I think I can put one here, right? Because that diagonal is open, and that diagonal is open. Cool, so we put a queen there. Now we're in the next column. Can we put one here? No. Here, no. Here, no. Here, no. Here, no. Here. Let's see, can we put one here? This diagonal, Nope, that diagonal's a no. Let's check the next one. How about this one? Nope, can't put one there. How about this one? No. Uh-oh. We have reached a base case, right? Our base case was either we solved it or we're stuck. So what do? Now this is what we're going to call the backtracking pattern, right? So if it doesn't work, what I need to do is say, oops, no solution, rewind, go back a step and say, oh, okay, well, obviously this queen here was no good. I can't have a queen there with the solution. So I'm going to undo it and say, oops, nope, no queen there. Boom. And undo all these X's because we'll go back. Okay, and then we'll try the next one. Can I put a queen here? No. No queen there. Can I put a queen here? No. No queen there. Go in here. Nope, not there. Not the diagonal. How about a queen down here? Sure, I can put a queen down here. So it tries, using this recursive backtracking pattern, to keep on putting queens on the board. And we'll say here, no. 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 And here, no. Oh, well, we couldn't put a queen there either. So that was no good. Okay, so backtrack. That was no good. We'll go back. So this queen was no good. So an X there. It says, oops, well, I can't put a queen there. So this queen here must be bad. So let's backtrack. That's no good. Let's undo all these. Okay, so then we'll try here. Can't put one there, can't put one there, can't put one there, can't put one there. How about over here? Let's try over here. Sure, that one's open. Now let's see, can I put one here? Nope. Can I put one here? Yeah, that one's open. We'll try here. So we're going to keep on trying over and over and over and over and over until we find a solution that does work. And anytime we either hit a dead end, or if we hit the dead end, we backtrack. We say that was no good, we go back. Or if we reach the base case, we're done, we solved it. The other base case. Okay? So our algorithm here was put queen, or it was, we were saying for row 0 to 7, try queen. In column, number of queens. That was it. That's essentially it. So it looks like a harder puzzle than it actually is. It's not too bad to solve. Okay, and to do this, we're going to write a class for it. We'll call it nQueens. And, sorry, we'll get back to that in a minute, how we can actually use n. Okay? So, we're going to define an init. Init's job is to set up all my values. So I'm going to have a board equals a 2D list, right? And then I want to say for row in range 8, self.board.append. We want to append in another list. Okay? And then for column in range 8, we want to take self.board at row, and we want to append. In our case, I just want to append a space. Now, I know there are better ways to do this. We could do some list comprehension stuff. Depending on how you like your 2D lists, this may or may not be good for you. Okay? And doing your list comprehensions. Not too big of a deal. Right? We got lots of ways of doing this. But I'm partial to this, because it, sure, might be a slightly bit slower, but that's okay. Okay, done. Now we have an empty board. Now we'll have a self dot number of queens on the board is 0. I currently have 0 queens on the board. Right? Because we're tracking. That's my counter. That's how I know when I'm done. Okay? Do we need any other values? I don't think we were tracking any other values. Okay? Then we're going to have that recursive method called solve. So solve is going to do that thing. So we're going to say for row in range 8, right, which will give me 0, 1, 2, 3, 4, 5, 6, 7, 8 values, right? Indexes 0 through 7. We're going to try and put a queen in. Right? So we're going to say if, I don't know what, self.can. And these I'm going to make private helper methods because they don't really need to know what these methods are. You know, can put queen. And then can put queen needs to know what the row number is. So if we can put a queen there, let's put a queen there. Okay, so we're going to take self.board at row at self.number of queens on the board. Because remember, we're always going to drop it in that column number. Right? When I had 0 queens, I dropped it in column 0. When I had 1 queen, I dropped it in column 1. When I had 2 queens, I dropped it in column 2. Right, that was my shortcut here. We're going to say it equals a queen. Right, put a queen down. Okay? Once we put a queen down, we want to recurse. Self.solve. Right, this is the recursive call. It calls itself. We're calling solve again. But before we do that, that's right, self.number of queens. plus equals 1. Add a queen. Right? This will try and add the next queen, 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 and add the next queen. Right? What we're missing now is the backtracking portion. So if solve gets stuck and I can't put a queen down, because remember when we make function calls, like when we did Fibonacci, they went on that call stack. Let me do it like a new page here. Let's see. Sure, over here. Right? We said like, let's just do countdown. So we had like count of 10. Right? So we stored off, we said, okay, we're counting, and it's 10. That one called count at 9, which called count at 8, which called count at 7, count at 6, on and on and on. And they all got saved over in this call stack. 8, 7, 6. And when one function is done, when it comes off the stack, we go back to where we were at that previous line number. So if solve gets called recursively and it can't put a queen down, it's going to come back to solve here. So now we need to backtrack. We need to undo. So we're going to do these 2 steps in reverse. Right? Put it back to a space and take one away. But I have to do them in the reverse order. Here. Sorry, give me just 1 second. Apologies. Sorry, the little guy downstairs is quite the daddy's boy, and he's sad that I'm up here teaching. He understood it better, I think, when I would actually like go onto campus. But now that I don't actually leave the house, it just makes him upset. Hey, Zoiku, thanks for coming along. I'm doing some backtracking recursion here. So this is the undo step, right? Remember when we said, okay, well, if I can't put the queen here, undo it. That's what we're doing. We're undoing. Okay, we're just going to continue on. So the other piece here then, right, in solve, we need to make sure that if self dot number of queens on the board is equal to 8, we want to just be done. Right, we won. We beat the game. So we'll say, you know, let's do this. Let's have another value here. Self dot is solved is false. So if it reaches 8, we'll say solved is now true. And then we only want to do this if not self is solved. I don't know, I feel a little bit bad about that, but that's okay. So we only want to keep trying if we haven't solved it yet. This will stop the recursion from happening. Right, this is it's sort of like a break, but if we just hit return, we're going to keep undoing all the things we just did, and we're going to keep going. And if you know anything about the 8 queens puzzle, there are 92 solutions. We only want 1, right? I mean, maybe we wanted all 92 or something, but for now we just want to stop when we find 1 solution. So we're going to have a flag here and say, okay, we're solved, and only do this if we're not solved. So this is, in the recursion, remember we need to check for the base case. Did we reach the base case? The other base case is if we can't put a queen on the board, the recursion will just stop, right? If we can't put a queen down, we're done. Okay? Then the last thing we need to do is actually figure out how to figure out this function here. So can put queen down given a row number. Right? So we need to see, is there already a queen in that row? Is there a queen on the diagonal up and a queen on the diagonal down? Okay, so we're going to return, we can put a queen if self dot row is clear, given a row number, and self dot diagonal up is clear, given a row number, and right, do this functional decomposition thing, break down the problem smaller and smaller and smaller. Self dot diagonal down is clear, given the row number. Okay, that's it. So we're going to break this up into 3 different helper methods. Sure. So row is clear, given a row number. Define self and row. So how do I know if the row is clear? Well, I'm going to return if queen is in self dot board at row number, and I'm going to return not that, or queen not in, maybe. How about that? I think that's valid. Not queen in, queen not in. So if there's already a queen in that row, right, because I know I'm just putting Qs in there, then the row is not clear. So if there's not a queen there, the row is clear. Right, so how about the diagonal up? So define self and row. Now this one's a little trickier, okay? So given a row number, I need to check the diagonal up. Right? So let's say if I'm here at row 2, I need to check the diagonal up. So I need to go until I either I'm past column 0 or I get above row 0. Right? So in this case, I just need to go to here and there's nowhere else to check. If I'm over here, I need to go to here and there's nowhere else to check. Right? So either hitting row 0 or column 0, if I get past that, I'm done. So what I'm going to do is I'm going to loop. So I'm going to say for current row equals row minus 1. I'm sorry, let's do current row. We'll say current row equals row minus 1. Because that's the first one I need to check is back upper row, right? And then current column equals self.number of queens minus 1. Right? Because we're checking diagonal up. So we don't need to check our current location, right? We need to check the diagonal up location. So go back 1, 1. And then we're going to loop. We're going to say while current column is greater than or equal to 0, and current column is greater than or equal to 0. As long as they're both greater than 0, I can keep on checking. So I can say if self.board at current row at current column, if it equals a queen, return false. Right? That was no good. If I don't return false, take current row minus equals 1, and take current column minus equals 1. Okay? If I hit a queen, return false. That diagonal is not clear. If I've looped all the way through, and eventually I get to where I'm no longer greater than or equal to 0 on either the row or the column, I can return a true. Sorry, capital T. I keep forgetting that. Does that make sense? Right, so checking the diagonal up, right? That's going up a row and back a column. Up a row, back a column every time. Check up a row, back a column. Up a row, back a column. From wherever we are. And we just keep on going. If we find a queen, we return false. If we don't find a queen, we keep going. And if we hit out of bounds, we know it's clear because we've checked the whole thing. Right? So we're going to do the exact same thing here with diagonal down is clear, except now row goes plus 1, right? Because down is plus rows. So then while current row is less than the length of self.board, right? So still column, we can't get behind column 0, but my row, now I'm going to be checking downward. So right, if I'm here, go plus a row number, or over here, plus a row number, plus a row number, plus a row number, plus a row number. Right, from over here, plus a row number. Oh, I ran out of rows. My row got too large. No good there. Does that part make sense, how we're just breaking up this check here? Okay, and if we don't hit a queen, then the diagonal down is clear. So if we can put a queen there, if the row is clear, the diagonal up is clear, and the diagonal down is clear. If any one of those is false, the whole thing is false. We can't put a queen there, right? We're anding. The last thing we want to do is figure out how to print or turn ourselves into a string. Why not? So let's define the string function for ourselves. Right? So we need a result or something like that is a string, and they want to say for row in self.board. Results, I don't know, plus equals the row plus a new line maybe. So this way we get one row at a time and a new line and a new line and a new line and a new line and a new line. Then we can return result. Let's try it. So that's my class here. Let's rename this one here. So rename refactor rename. We'll call this nqueens. And then I'm going to add a new Python file, like main or something. Sure, why not? Add, doesn't matter. So in here, we're going to import. So from nqueens, import nqueens. And we'll make a new nqueens. We'll say, I don't know, my puzzle equals an nqueens. We'll call puzzle.solve. And then we want to print the puzzle. Right? Do all those things. We'll see if it works. Oh, dear. Can't concatenate a list. That's right. So the list itself we need to treat as a string. So turn that into a string. That ought to work. Because if we're printing, we automatically get the string conversion. If not, we don't. Uh-oh. Well, we got an empty board. Solve. Let's see. I don't know what happened. Let's for fun. Let's print self every time we hit the solve function and see if we can get something going here. Okay, and then you know what? For fun, I'm also going to take result. I'm going to add one more new line to make these things separate, just to make it a little bit cleaner here. Let's run that. Okay. All right, cool. Hey, look at that. We're getting there. We got a bunch of steps here. I don't know how well you can see that. There's one queen on the board. There's 2 queens on the board. 3 queens on the board. 4 queens on the board. 5 queens on the board. Oh, we had to backtrack. Right? We came back to here now. And we tried it again. Nope, no good. We had to backtrack. All right, so now we're here. Got another queen on the board. Oh, we had to backtrack again. Backtrack again. Let's see. So why did it stop? I think we must have done something wrong. Let's see. Keep on looking. See if we can get a queen in that last column. Sorry, I'm just looking through here. I think I might have missed something. Okay, there's a queen in the 7th column, or the index 6. We're backtracking. I feel like we got one, didn't we? You guys are awfully quiet in chat. I hope the stream's still working. It looks like it's okay on my phone. Come on. A whole bunch of attempts. Okay, thanks, Oku. Trying to find the one that worked. Huh. It should have found a solution sooner. I think I did something wrong then, because it should have found a solution before it moved that queen off the first corner, I thought. I wasn't watching the first position. Let's see. Okay, so something must be wrong here then in my Ken place. Right? Row up through range 7. Column. That should be fine. Let's see. I went too far. This is what I get. That's okay. All right, we're getting close. There we go. So here's our next position. So we tried. Okay, so it thought it couldn't fit any more here and had to move that first queen. That should be wrong. We should be able to fit another one on. Right, because that first solution has a queen down here, which is like 0, 0, if you like imagine it flipped. Sorry, it's like this, but flipped upside down, I guess, or like this. There's lots of solutions with the queen in that bottom corner. Because if you imagine this is a solution, you just make a mirror image of it and flip it over, and then the queen's there at the top. Look at that, they even like label on there. Nice. So should I be able to do that? Yeah. Where we had another queen on the 7th row. Let's see. So right in here. We should be able to find a solution. Right, queen on the 7th row. Flipping it. Hmm. One, two, three, four, five, six, seven, eight. Okay, that's right. I did the right numbers. 1, 2, 3, 4, 5, 6, 7, 8. That's the right numbers. Hey, Blowfish, thanks for coming by. So that's clear. That one's clear. I think that should have worked. Somewhere right up in here, right? I want this image but flipped is what I want. So I never got that last queen there on that 3rd row. So debugging this is a little bit trickier. Let's see, can put queen. Maybe I did something wrong with one of these. Okay, then I put 0. Yep. If it's a queen, return false. Current row, current column. Current row, current column. Current row is less than... Oh, this needs to be... Oh, that should be okay. As long as we check them. This logic here. I forgot. This was a bad copy-paste. My mistake, folks. Right here. Current row needs to go +1 because we're increasing the row number. That's the problem. All right. That ought to do it. I found it. Found the problem. And let's run that. Uh-oh. Took them all off again. Let's print self. If we're solved. Let's see if we can print ourselves here. So, because it's coming back. It's still undoing. Here is the problem. So when we come back from that recursive call, we're still inside of this for row and range. So it's undoing all of those steps. We don't start a new one, but we're undoing our problem. We're undoing ourselves here. That's what it is. There we go. There's a solution. Look at that. Thought we could get one. So if you do the logic right, you can solve it. There we go. So that should be one of these solutions here. Flipped, right? Boom, boom. Should be 3 in a row that way. Where am I missing? Which one of these is it? I don't see it. I had in my check for diagonal down where I had copy pasted. Here, I forgot to be increasing the row to keep going downward. So it was checking incorrectly. It was just a bad copy paste. Because as we're going diagonally down, we're increasing row number until we get off the board, instead of decreasing row number until we get off the board. So if we wanted to, right, if we stop this, if we don't stop when we're solved, we could print all of the solutions, which is kind of fun. If we wanted to get all the possible solutions, we'll just keep going forever and just print every time we get solved. Really, we don't care about solved here. We'll just print ourselves. Now when I run, I should get all 92 solutions. And look at that. That's beautiful. Look at all those solutions. Okay, and we could count here, right? We could even add a counter. We could have a self.solution count is 0, and every time we solve it, we'll take self.solution count plus equals 1. Right, and then when we're done, maybe instead of printing that, we'll print puzzle.solution count. 92 solutions. We proved Wikipedia correct. And this is relatively quick. This is relatively quick backtracking solution here. And it's a limited scope, like a limited size here. So now to make this, and well, so let me say, is that clear? Does this make a little bit of sense of what we were doing here? first before we move on to another topic? All right. Trying to watch chat here on my phone. Okay, cool. You're good with it? So now what we can do is we can actually make it variable on n. So what we need here is we need a size. So in the constructor, we want a size. Sorry, so we don't need the parentheses up there. So instead of range 8, we're going to go for range size. Range size. So I'm pretty much going to search here. We're going to need that to be a self.size is the size. So anywhere I had an 8, now I want to use self.size. So if I reach the size number of queens, great. If I reach the size number row, and this one we don't even need to use size, we can use length of self.board. It's probably even better than size, because we know that means the same thing. And then I think that's the only place we have 8 in there at all. I'm going to put this one back in, because I don't, the larger you get, the faster it is. Not the faster. The larger you get, the more solutions you can have. So I want to stop after one solution here. And let's try an n queens of, say, like size 10. So if we have a 10 by 10 board, I can still fit 10 queens on the board. Right? If I have a 16 by 16 board, we can fit 16. Notice that was a little bit slower. Again, still relatively quick, because at most, like the recursive depth, how many recursive calls we have is 16, because there's only one per column. 1, 2, 3. We're with like Fibonacci. I mean, even that didn't get super deep, but it had to do it so many times. So at most, now we're doing 16 checks, and then each one of those, so 16 for each column, and each one of those could run 15 times 15. So I think it's, what is that, factorial growth at this point? Because of the 16 checks here, all of them will check now 15 by 15 check, or 16 by 16 checks or something. It's a big number. It's a big number, but thankfully our computer is relatively quick. You can learn about how you actually measure. Oh, there we go, 20, and now we're having trouble. Oh. So it's solved. It just took a little while, right? We could go even bigger, maybe like 24. Yeah, max depth. Yeah, Python does have a stack. And you can change the max depth. So our depth is never going to go super far, because it's just the max number of columns. Because we'll eventually hit the backtrack and unwind soon enough. But okay, so for fun, let's put a breakpoint in here. I want to show you in debug mode. This is poor man's debugging, because it's really tedious to do this tons of times. I'm going to put an if statement in here. Say self.number of queens on the board is equal to 23. Print something, sure, it doesn't matter. But here I want to put the breakpoint, because I only want the breakpoint to happen if I get to this certain condition. It's poor man's debugging, but it's okay. So now when I debug my code, right, debug main, it's going to stop, and we can see that call stack, which is really fun to look at. There it goes. So now we have 23 queens on the board. So this is the call stack over here on the left. We'll see this was the original position, right, where row was 0, row was 2, row was 4, row was 1, row was 3, right? So remember, each recursive call needs to track all of the variables in that function. So thankfully for us, inside of solve, the only variable we really have that's not an instance variable is this row loop here. So it needs to track what row it is. So that way, when we are backtracking, we say, okay, we tried row 18, that was no good. Now let's go back to the for loop. Hey, give me row 19. Right? And we go on and on and on. And you see all the different rows in here eventually. So this call stack's not super big. So it's not a very deep call stack, but it spreads really wide really quick, because each one of those rows then has to do every other attempt. So backtracking solutions are not necessarily the best solutions in the world. Right? But they're one approach. It's a very naive approach. If you want to take the AI class, you can learn more about better solving solutions for things. This is just naive. And that's okay. I'm not too concerned about it. Do I need another 2 new lines? Sure. So that's our queen's puzzle, n queen's puzzle here. Wait, we can get smaller. Let's try. I think you can solve a 4. Okay, you can solve a 4. I don't think you can solve a 3 though. Yeah, you can't solve a 3, but you can solve a size 4 puzzle. Okay. It's solve a 5, right? It's just fun. So, and I think we could just, let's do that. So for n in range, let's go up to like 40, maybe. Actually, we want to start at, let me say, 4. And we actually don't need the solution count. We only want to print puzzle of n. Right? So while that thinks about the bigger puzzles, right, we see the smaller puzzle solutions getting bigger and bigger and bigger. Notice they look kind of similar, which is cool. But I don't know if there's an actual mathematical pattern in here. That's a good question for some of our math friends, if there's a pattern in here. But it's just going to keep going. It'll keep trying to solve. That one is 20 lines. See if we get a solution for 21. 21 must be harder. You guys doing okay? All right, cool. Okay, awesome. There's 21. Oh, wow. I don't know what it's doing right now. It's freaking out. Okay, I'll just stop it. That's fine. We got some solutions. This was 22. Okay. So that's n queens. Again, this is backtracking recursion. So we're going to attempt, and if it doesn't work, we undo. So that's a key step here, is the undo step. Okay? This code, exclam GitHub, should give you the link to my GitHub repository, and I'll make sure I actually push all that stuff out. 2001. Be the right semester here. It's n queens. I'll commit and push. Yeah, exclam GitHub ought to give you the command there, or the link. It should also be in Canvas as well, unless I messed that up. Possibly I didn't put it in Canvas. Oh, I think it's in the modules, isn't it? Or no, it is a... No, it's not. Shoot, I'm sorry. I don't know, let's put it up here maybe. We'll do a external URL. Okay. There's the URL, this is the course GitHub repo. I feel like I have it somewhere, but I don't know. That's weird. I'll put that at the top of the lecture archive. Okay? Oh, exclamation. So it's the shorthand for it. I'm too lazy to say exclamation. Just I usually make fun of people for doing stuff like that, but yeah, my apologies. It's is that slang maybe? It's exclam slang. So I'll put the link here in Canvas. Sorry, I thought I had that out there before. No, so like you can just click the link and it should take you in a new window, of course, out to here, and then you can look at all the different things from there. Yep, does that make sense? Cool. Cool. Okay. So we've done inheritance and testing. So what we're going to do is we're going to do some testing with our project as well, because we want to make sure that any code worth writing is worth testing. Let me go back here. Let's start up project number 1. All right. First project. Project 1. This is Backtracking Recursion. And we'll do 2 weeks for this, so the 28th to the 10th, 11th here, right? 11th, specifically at 3:30, because at 3:30 on the 11th, I'm going to go over my solution to it, and from that point on, I won't be able to take it. Okay? Okay, come on, let's load. And what you're going to submit is, nope, not paper. Nope, online. What's the URL? You're going to submit the URL to your code in github.com to me for this project, just like we're doing for the labs. Just give me the URL for it here. Okay, so we're going to create a backtracking maze solver program that will calculate, I don't know if calculate's the right word, whatever. Calculate the shortest possible path for the maze. So some mazes have more than one solution. So we're going to make a maze class that accepts a 2D list as the maze to solve. Use backtracking recursion. Solve the maze and track the shortest solution. Okay, so this means we're going to have to try every single possible solution. Like when we found all 92 solutions for n queens, you're going to have to find every solution and see which one is the shortest. So you'll have to track some information about it as we're going. Now, I know there are maze solvers. I'm not dumb, right? You can Google Python maze solver. Okay, I know those exist, right? If you give me one that does an A* search, we're going to have some problems. Okay? I don't want you to take the maze solver from online that's actually good and efficient and give it to me. I want you to use the crappy recursive backtracking one. Okay? It's not hard, I promise. Okay? Don't use Dijkstra's algorithm. I should really be able to say the guy's name. I'm sorry. It's not good. This one opens up CSV files. It plots. Yeah, you don't need to do any of that stuff, okay? Trying to find a solution online is going to be more difficult for you, I promise. Okay? So, don't give me one of these. All right? I know they exist. Don't give me one, especially one that is not backtracking recursion. Okay? Please. So, do not give me a solution you found online. Like, don't even say, like, cite my source for it, because that's not what we want to do, right? The goal is to handwrite this and understand how it works. Understand. There's an R in there. Okay, understand how it works. So, part of the points you're going to get for doing this is we're going to meet up individually. There's not too many of you folks, so we can meet individually, and you will describe how your program works. If you can't describe how it works to me, it won't go well. Okay? You will describe how it works to me. And if you can't, it will not go well. Okay, does that make sense? Is that fair? Right? So to do a maze solving program, right, we have a 2D list, which is a maze. Right? Here's a row, here's a row, here's a row, here's a row, right? An empty space is probably somewhere you can walk. Right? If you have an X in there, that's probably a wall. You can't walk on the wall. Right? If you have an S, that's the starting position. If you have an E, that's the ending position. Let's see. We want more than one solution here. So let me actually open this up. X, Oh, this is too small to have more than one solution. Okay, let's do this. Let's do this. I can solve it. We'll start here in the corner, and we'll have some X's over there. Yeah, that's too small. Hang on, I need one more row to add another little loop here, right? So there we go. So if we have a 5x5 maze, that ought to do it here. 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so if we start there and end here, like the shortest possible path is probably just going straight here and down. But we need to be able to solve that with our program. So we're going to make a little path here. That, oh, is that even big enough? It's not even big enough, is it? Okay, yes it is. Nope, we need one more row. Sorry. We'll get there. We'll get there. Because you have to, like, snake through this thing. X. Okay, we can just do it with just one more row there. That's fine. Sure. I'm going crazy. Sorry, folks. Need a lot of rows. Okay, need more rows than that. Sure, you know what? That's just fine. If that bottom row is empty, that will take up more space. All right. So when you create the maze, right, the constructor for it accepts a 2D list as the maze. So the init method will take a 2D list. So I should be able to give you any 2D list. And when I go to grade this, I'm going to have a bunch of 2D lists already set up for unit tests that I can run, and I'll make sure I get back a value. So solve should set a value like maze solver dot shortest path steps to the shortest number of steps, shortest path count or something like that. Does path count make sense? Shortest path step count. So for this maze, right, if we start here, whoa, right, this is a step, this is a step, this is a step, 4, 5, 6, 7, 8. So it took 8 steps to solve that direction. This way is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That path was 10. Okay, so that was no good. Does that make sense? So the first one was 8, the other one was 10. I mean, you could also go like this direction around and you'd have 4 more steps would be like 14. That'd probably be no good. Or you could come this way and go and just have 12 steps. Right? So we got a couple options. But our maze solver needs to try every single possible solution. So remember, a simple backtracking solution, 2 base cases. Right? The base case is we got to the end. We're done. Right? If we got to the end, we're done. If we didn't get to the end, the other base case is no move. Right? Either no move, we're stuck, time to backtrack, or we got to the end, we're done. Again, we're still going to backtrack, but we reached a base case, right? Track that as a solution. If we haven't got to a base case, what do we need to do? Well, you can try up, you can try down, you can try left, you can try right. Right? Any order you want, and it shouldn't matter, right? Because we want to try them all exhaustively anyway. So that's the algorithm. Is try up, try down, try left, try right. Same idea. Make sure you don't go out of bounds. And like when we placed a queen, you can't walk on an X. I just need the shortest solution. So your solve, you should have like a shortest path steps or something. Shortest. And that's what we're going to check. So that's what we can check. Did it calculate the proper shortest path? So a couple things. In a maze, it's possible, if you're not careful, that you go, okay, I'm going to try up, down, left, right. Up, down, left, right. So if I'm here and I go down, the next thing I'm going to try is from this position to try and go up. You see a problem with that? So if I'm going to go from here, I'm going to go down, and I'm going to go up, and I'm going to go down, I'm going to go up, I'm going to go down and up, down and up, down and up. So what you have to do is, just like when we were doing the queen's puzzle, we marked the board. We said, oh, put a queen on the board there. You want to put something like Hansel and Gretel that says, oh, I was here at this space. So when you say, can I go up? You check to make sure that it's open and it's not a breadcrumb or it's not a wall or whatever your condition happens to be, right? Does that make sense? So you want to make sure you don't get stuck in one of those infinite loops where you're going up, down, up, down, up, down, up, down, up, down, up, down, up, up, down, up, down. I can't even, doesn't even make any sense anymore. Cool. So then the other piece, right? We have these class level attributes. So in our case for like queens, we were like solving this, we were counting the solution count occasionally. I think we were still doing that, right? Yeah, solution count. But we would stop. So you don't want to stop when you're solved. You want to keep on going. But instead of tracking solution count, you want to probably track your number of steps, and which is the max number of steps. So when you reach a base case, like, hey, I solved it, you probably want to be recording that number of steps and comparing it. Because we only care about the shortest number of steps. I don't care how many solutions there are. I don't care about longer ones. I just need to know the shortest number of steps. So if you find a solution and it is more steps, I don't care. You don't need to save that. But if you find a solution and it's less steps, yes, you want to save that. Okay? So we've got lab on Monday. We're going to practice recursion in lab on Monday. We're going to have some fun there for the Monday lab. Your lab from last time isn't due yet, but make sure that gets done and we can do stuff in GitHub. Again, we went over it on Tuesday. I'll typically go over labs on Tuesdays. The goal is that you get them done, but if you just wait for me to give you an answer and then you turn in my answer, you're going to get points for it, but it's not going to help you at all. Right? The goal of having that lab time is that it's your time to practice. Is that fair? So I want everyone to get them done, and you'll get points for getting them done, but if you're not solving them yourself and spending the time practicing, it's not going to help. And then when you get to these projects, they're going to be way harder. And I don't give solutions for projects like I do for labs. I mean, I'll go over a solution, but I can't take it from you late. Whereas the lab, I can still take it from you after I've showed you a solution. Because the goal is you get the lab done and practice it. That's your practice time. Okay? Cool. That's all I have for today. If you guys want to take a couple minutes to start on it, or, I mean, whatever you need here. So we're also going to include unit tests for your maze solver. Okay, so I'll post a rubric for it. So you get points for the unit solver. You get points for the wow. Points for solving the maze, and you get points for the unit test for doing it. So if it looks like you copied one from online, you'll have to explain your solution to me. If it looks like you wrote it yourself, I probably won't ask. Is that fair? Again, you guys are allowed to discuss things with each other, chat about it, but as soon as you like start taking notes and be like, okay, this step, this step, this step, this step, write it all down, we've gone too far. Okay? Yeah, the 2D list. So it's a list of lists here. And you get at things by row number and then column number, column index. So let's like maybe pull up one of these smaller ones here. So in one of these smaller boards here, like this 4x4 here, right, this is the board index 0. This is the first item in the list. The thing in the list happens to be another list. So I have 4 items in my self board list. Each item is another list of 4 characters or 4 strings. So to reference a position, it's row index, column index. So this is 0, 0. This is row 1, column 1. This is row 2, column 2. This is row 3, column 3. And typically, when we do lists in Python, right, we just append to them because they're resizable. It's not fixed like an array. Yeah, so I just call it row and I call it whatever. It's any number. A lot of people like I or R, like they'll use for I in range because it's an index value. Maybe better to like, let me rename this here. In fact, to rename, this is row index. That's the index. Sure. I mean, row index, row number, I don't know. Maybe it's fine as row, but that's the number here. That's representing the number. Yeah, so it's just my terminology for it. So like this, we didn't use column, we just used number of queens on the board because that represents the column index. Because when I have 0 queens, I'm putting queens in that first column. When I have 1 queen, I'm putting it in the 1th index column. Because this is column index 0, this is column index 1, column index 2, column index 3. Because you always have indexes between 0 and up to and not including the length. Cool. All right, gang. We'll be around Monday for lab time then, and we can go from there. I'll post this rubric a little bit later for you guys, and then I'll post the quiz as well for recursion. I just have to get those posted. Okay? If you have any questions, hit me up. I'll be around on Discord for office hours after class, and we can go from there. All right, take care.